listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists. And they're going to shine a light on some interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. In one of our recent webinars, Stefan Schultz, a field application engineer with Worth Electronic, explained why common mode chokes are widely used in noise suppression for a variety of applications. Now, while we mostly understand the reasoning behind common mode chokes, we might not understand how to properly select the right one for specific applications. Well, for a better understanding, Schultz described the main datasheet parameters and charts in detail, and also demonstrated how to simulate common mode chokes using software tools such as LT Spice. Enjoy today's What's Up podcast with Stefan Schultz and our presentation, Common Mode Choke Parameters Explained.
First, I would like to introduce the topic by speaking about some core materials, especially ferrite materials, which are usually used for common mode choke products. Then we will have a look at core shapes which are existing in principle and what are the differences between them. And the last part and the main part of this presentation will be about the main parameters, how they are measured, how they are determined, and what are the relations between them. So first, let's look at some core materials, and I would like to start with by repeating what is hysteresis. So maybe you know from your physics study or from school that each magnetic material or ferromagnetic material has a hysteresis. So if I bring it into a magnetic field and I change the amplitude of the magnetic field, then the flux density inside the material changes in a nonlinear way. And here in this diagram, I have compared 3 different hysteresis cycles of 3 different materials. The first 2, in green and red, are the nickel zinc and manganese zinc standard ferrite materials. These mixtures are usually and widely used for suppression elements, also for power products, power inductors and transformers. But here especially we speak about materials which generate losses and which are used for noise suppression. And the third one, which you see here in yellow color or orange color, is a nanocrystalline material, which is not belonging to the class of ferrites, which is a specific material which has a usually very high permeability. This can already be seen when we look at the central part of this diagram, where the transition from the negative field level to the positive field level is quite steep. And this transition or the slope of the transition indicates and is proportional to the permeability of the material. So when it's very steep, the permeability is high. What advantage we have? If we have a core with high permeability, its advantage is that we don't need so many winding turns in order to achieve a certain inductance. So winding turns can be reduced and wire diameter can be increased, for example, and we get a higher rated current in the end. So what are the typical value ranges for different ferrite materials and the nanocrystalline material which we use in our products? So the nickel zinc ferrite, which is consisting of nickel oxide, zinc oxide, and iron oxide, mainly in a different mixture. So we can reach initial permeability values or relative permeability values up to 800. If we need higher or want to have higher permeability values, then we have to use manganese zinc mixtures, where it goes up to 10,000 as a factor. And the highest values we can reach with nanocrystalline material, here we have a maximum 95,000, but in general you can get materials up to 200,000 as a factor, but those are for specific applications. And then there are components existing which combine different core materials. In this case, you see the EXP series from us, which has two cores. One is made of nickel zinc, and it has a permeability of 400, combined with a manganese zinc core, both in toroidal shape, and it has a permeability of 6,000. So with this combination, we can achieve a higher or wider broadband frequency noise suppression. So in principle, we can say that nanocrystalline material, which has a highest permeability, but it's for the lowest frequency ranges up to several hundred kilohertz. Then the next higher frequency range will be covered by manganese zinc cores, so roughly up to 20 megahertz. And everything above 20 megahertz is then covered by nickel zinc cores. So this can go up to several hundred megahertz depending on the permeability and of the construction of the core. So let's look at some core shapes which we find in general on the market. So first for mains voltage or mains voltage chokes. So this is very common shape here, the vertical oriented toroid with for one phase choke with two windings on it and a separator to increase the creepage and clearance distances between the windings, usually mounted on a base plate and as a THD product. This is the open construction. If I put it into a plastic housing for insulation purposes, then we find this shape, for example. And then it's possible to orient the core in a horizontal manner, just to save height in your application, but you need a larger footprint, more size on your PCB. The horizontal core has the advantage of having a lower parasitic capacitance between the input and output terminals compared to the vertical oriented core. Here's a smaller core also already inside a plastic housing. In the center, we see the so-called frame cores, either without a center leg, like shown here, and a rectangular cross-section, where the windings are separated on two different legs, on two opposite legs of the core. Or sometimes we have the frame core with a center leg, but without any air gap inside, and the windings are placed on the center leg side by side. The same as we can find here on the vertically oriented core, frame core, at this part specifically, or in a larger size, like seen here on the right side. Again, a frame core with a center leg and the two windings in parallel on the center leg. For low power applications or for data line noise suppression, we usually find smaller combo chokes, again with a toroidal core inside, so here on the left side, which is usually horizontally oriented and molded inside a plastic housing. Then you have the vertically oriented drum core, mostly shielded one. It has a ferrite shield on the circumference. Then the so-called H core with a plate on top, this ferrite plate which is glued onto the core. And this can be automatically wound very easily. If we use a block core and with a slit inside, then we can feed through, for example, flat wire winding into this core, and it's a very robust construction and compact. But with this combo choke, you cannot achieve a high inductance because we usually have only one winding, one loop of the wire through this core. And on the right side, we see ceramic substrate with integrated conductive material, but this is intended to be used for higher frequency noise suppression, so in the gigahertz range, for example. So let's come to the parameters. Here we see an overview about the main parameters, which I will speak about subsequently. First one, of course, is the main inductance of this component. And in the datasheet, you find a table where the main inductance is indicated by the symbol L. And it's also written how much inductance we have. So in this case, in this example, each winding has 2.5 millihenries with a tolerance of plus minus 30%. And this factor of 2, which is written here, indicates that there are two windings with equal inductance of 2.5 millihenries. The inductance is measured at a certain frequency range, or frequency, fixed frequency, and with a certain current amplitude, in this case 100 microamps. How we determine this inductance? Just by using an LCR meter, which is attached to each winding separately. And the other windings, or in this case, if a one-phase choke, the other winding is left open. If I would make a loop here or connect both ends of this winding additionally, then I would have a transformer principle, and I would also measure the mutual inductance, which I don't want to. So it's left open. And of course, the inductance of both windings should be quite similar or equal to each other with inside the tolerance band. Here you see a view, a picture of how it could look like, the measurement, with the LCR meter in the background and the two terminals connected to the wire, to one winding. Next, and related to the main inductance, is the so-called leakage inductance or stray inductance. For this specific example, which I've chosen here, there's no information given in the datasheet, but I will show you later how it's possible to calculate the leakage inductance from the differential mode impedance curve. In principle, it's possible to measure the leakage inductance by short-circuiting one end or one side of the common mode choke, like shown here on the right side, and connect the LCR meter on the left open terminals. In this case, the main inductance is compensated, and due to the opposing currents flowing inside the windings, and only the stray field is acting. So for perfect coupling, the coupling factor would be near to 1. Of course, it would be, perfect coupling would be 100%, and the K factor would be 1. But in reality, we find values from 95% up to 99% or 99.5. But 100% it's not possible to reach. So the higher the coupling factor, the lower the stray inductance. Also shown here how it's measured. And you see on the right side here's the connection to the terminals of one side of the windings, and here in the background this is the short circuit connection of the output side of the choke. Related to the leakage inductance is the winding structure. So in principle, there are different types of winding structures possible. On the left side, we see the so-called sectional winding, where we have a separation of the windings on the core. So it's a geometrical or spatial separation, and mostly also added with a separator between the windings just to increase the creepage and clearance distances. The sectional winding has the advantage of not having a higher weighted voltage, because the windings simply the wires are simply further apart from each other. So insulation is not that critical, and we can reach higher rated voltages. But on the opposite side, the stray inductance is higher, because the coupling of the windings, the further apart they are, the lower the coupling, the smaller the coupling, and the higher the stray inductance. So it can go up to 5% in maximum. On the other side, we speak about the so-called multifilar winding, or in the case of two wires, it's named bifilar winding, where each of the wires is tightly wound around the core. So then the compensation effect can take place in the vicinity of the wire. And if I have the same number of turns, the same core, like on this side here, then also the main inductance would be the same. But the stray inductance or leakage inductance is much, much smaller because coupling here is much stronger. This can be also visually seen on this page, which is a simulation. So we see here a cross-section of a toroidal core on the left side with the sectional winding. And the green color here indicates the field amplitude, the magnetic field amplitude, which is distributed quite equally here inside the core. And so extends further away from the wires. Whereas for the bifilar winding, we see that the magnetic field is only in the vicinity of the wires and rapidly drops if I go away from the two wires, just already in the center here of the core. It's very, very small. So for some match codes, for some parts, I have measured and additionally calculated the stray inductance. So this is summarized in this table here on this slide. So the first one is a data line choke or low voltage common mode choke, and the other four are mains chokes with a sectional winding. And there we find ranges roughly 1% or 0.5% up to 1.5% for the FC series. The SR2, which has a bifilar winding, it has a much smaller leakage inductance of only 0.1%. This equation which you see here on the top is how to calculate the stray inductance from the differential mode impedance curve. And the frequency, and I will show you an example later. The next parameter I would like to explain in more detail is DC resistance of the separate windings. So this is quite easy to measure. We simply take a milliohm meter and measure the resistance. So we are usually in the milliohm range. And again, in the datasheet, there's a factor of 2 indicated here, which simply says that there are 2 windings with equal maximum DC resistance. So the tolerance bound is always given the upper bound, so the maximum are DC. And the test condition gives you information about at which temperature, at which ambient temperature it was measured. So here's a test setup displayed right at the milliohm meter here in the background, which you can perform a 4-wire measurement, which is very precise. And related to the DC resistance, of course, is a rated current. The rated current of such a product is always given for a certain self-heating of the component, which in our case, for this example, is 55 Kelvin. The rated current has a symbol IR, index R. And how to read this line of the datasheet? If I apply a DC current of 10.3 amps, then the self-heating of the component is maximum 55 Kelvin above the ambient temperature. So again here, the upper bound, the upper tolerance limit is given. This is how we measure the rated current. It's like a similar setup like measuring the leakage inductance. We simply connect the 2 windings and put them in series. And then we attach the DC generator terminals to the to the open side of the choke, put everything into a wooden box, which in the end will be closed. And yeah, also the component is then observed by the infrared camera, which looks through the ceiling of this box. And the current is slightly increased step by step. We are waiting for a thermal equilibrium. And yeah, so in the end, we get a current or a temperature versus current curve. And if we reach a certain self-heating, then at this point, the rated current is red from the diagram. This is a closer look at an example. There's a small LF series SMT component where the two connections are visible for the generator. And of course, as you can imagine, first the winding heats up, and due to the thermal coupling, a bit later with some delay, the core also heats up. And related to the rated current is the so-called derating. That means if I increase, or if I put my component into an ambient temperature, which is above a certain limit ambient temperature, then I have to decrease the current flowing through the winding. So for mains filter chokes, mains line chokes, the limit is normally the 70 degrees Celsius, because we have a maximum operating temperature of our components of 125 degrees Celsius. And for 55 Kelvin, then it's just a difference. So the rated current is defined for 55 Kelvin self-heating. And so I have to reduce if I go above the 70 degrees. The reduction is not done linearly. Instead, it's a nonlinear behavior, which you will see on the next slide. So there's slightly a margin or a buffer which you have for the rated current. So this is valid for mains filter chokes. As I said, for some other match codes or some other products, the rated current is defined differently. So we find not only 55 Kelvin self-heating, but also 20 or 40 or 45, depending on the series. So you always have to look at the definition for the rated current and what value was used. So this is how it looks graphically. Up to the limit temperature, ambient temperature, which is here on the x-axis, we can apply 100% of the rated current, and then the current has to be reduced by this square root manner. But at the maximum operating temperature, which is reached here, for example, 125 degrees Celsius, the current has to be reduced theoretically to zero. That means no more current allowed. Of course, there are some margin, and you can still apply a small amount of current at this temperature, but we don't guarantee that the component will behave as intended at this temperature. You have to check it by yourself. The next parameter I would like to speak about is the rated voltage. The rated voltage is depending on the operating voltage of your system, where you want to attach this or want to use this common mode choke. Of course, the higher the working voltage of your system, the higher the rated voltage of the component should be. It should fit to each other. So in this specific case of my example here, it's an HV, it's a high voltage choke, and it has a 760 volts RMS rated voltage, which is measured at 50 Hertz. So it's a normal sinusoidal mains voltage. And so construction of the component has to be according to the standard, for example, the IEC 6938-2, which defines the minimum clearance and cleavage distances for such components, for such inductive components. And our products are designed according to these international standards. Then before releasing a product, we have to make a so-called stress test for the rated voltage. That means we put several components, equal components side by side, or actually in parallel, on a PCB. And then before we apply the rated voltage for 1 hour, we have to measure the main parameters like main inductance, DC resistance, and insulation voltage. And after 1 hour of continuous application of the rated voltage, we measure the parameters again, and there must be no deviation between them. So no alteration is allowed. And during the test, also the current is monitored to see if there is some sparks or some current leakage in the windings, which could be an indicator of having a fault inside the component. And the last main parameter I would like to mention is the insulation test voltage, which of course is related to the rated voltage. So also there's a factor between them given in the standards. So for this component, for example, it's 3 kilovolts RMS. There's an AC voltage applied with a frequency of 50 Hertz. And over a period of 2 seconds, the current is monitored, and it should not increase or go above 5 milliamps in this case. So according to different international standards, there are different definitions which we can find in those standards. For example, the already mentioned 5 milliamperes amps for 2-second application of the voltage, or 3 milliamps for a longer period, for example, 5 seconds. Yes, and this maximum current must not be exceeded. Here you see the test setup, one possible arrangement. On the left side, the high voltage generator with the 2 terminals here, and these terminals, the probe has some probe tips in the end of the wires, and this is then applied to the component for this certain period of time. And last parameters I want to mention are the so-called derived parameters. But first, the first one, the scattering parameters, which you normally don't find explicitly in the data sheet, only by choosing or selecting the separate files from the homepage, for example, from the online catalog. You can download scattering parameter files for some series. So meanwhile, we measure all our series on a special PCB with a vector network analyzer. So for the simplest component, combo choke with only 2 windings, you need a minimum 4-port network analyzer, and each port has its characteristic impedance of 50 ohms. And the modern network analyzers are capable of applying and measuring also the so-called mixed mode parameters. That means not the single-ended ones, which are related to 50 ohms, but also the common mode and differential mode excitation and reception of the signal. So with those capabilities, it's quite easy to derive the mixed mode scattering parameters, which are then arranged in this manner, like indicated here. So we have the reflected waves on the left side and the incident waves on the right side. And between them, the so-called scattering parameter matrix. In this case, it has 16 entries. So 4 of them are for the differential mode excitation and reception, 4 for the common mode reception and excitation, and 8 of them which indicating the so-called mode conversion between differential and common mode. So if those components are non-zero, then it's an indication of the symmetry, that there's no perfect symmetry of the component. So because we have here the most information we can get from those components, that means amplitude and phase, those scattering parameters are universal. Just to show an example how such a test board could look like for small data line chokes here in SA series. This component is soldered here in the center of the board. And here we see the 50 ohm trimmed microstrip lines with closure connectors on both ends, on all ends. Yeah, and so the board is normally then before finalizing the measurement is de-embedded, or has made a calibration before the final measurement. So we have only the scattering parameters of the component itself. And if I have measured the scattering parameters, I can derive several other parameters like the attenuation, for example. So again, differentiated and distinguished between common mode and differential mode attenuation. So common mode attenuation, we simply need the SCC2 one parameter, that means the transfer parameter from one side to the other. And in the logarithmic scaling in decibels, we can then have a frequency-dependent attenuation curve, which we put into the datasheet. And the same, of course, can be applied to the differential mode excitation. Then you have to take care of the so-called reference impedance. So for single-ended measurement, it would be 50 ohms. But for common mode excitation, it's 2 times 50 ohms in parallel. That means 25 ohms. And for differential mode excitation, it would be 2 times 50 ohms in series. That means 100 ohms. Then here is an example again for this product which I have used before already. How these curves look like. So in blue indicated is a common mode attenuation in the 25 ohm system in decibel scaling. So we see here the typical first resonance between 400 and 500 kilohertz. Then the impedance or attenuation drops due to the capacitive effect, because of the capacitance of the product. And for higher frequencies, we find those multiple resonances at equidistant frequency intervals. And the orange line indicates the differential mode impedance, in this case not impedance, attenuation, because due to the much smaller leakage inductance, it's also much smaller attenuation for differential mode, and it starts only above 1 megahertz in this case. So for lower values, it's only the resistance of the wire is active, and then skin effect and the leakage inductance take over and let the attenuation increase. And the last parameter I would like to mention is the impedance. Already spoke about this, but here if we have the scattering parameters measured for a component, we can simply calculate the differential mode and common mode impedance via the so-called chain parameters, this is chain parameter matrix, and the differential mode impedance, for example, is one of those 4 parameters, which can be calculated by using each of the scattering parameters for differential mode excitation. Of course, this is complex, and in the end, I have information about magnitude and phase, and usually we then take only the magnitude of the impedance and display it on a datasheet. This is then how it looks like. Of course, the curves are similar to the attenuation curves, especially regarding the resonance points, which are at the same frequencies. But of course, the scaling is different. Here we have a logarithmic scaling of the impedance. And we see already the much smaller differential mode impedance compared to the main or common mode impedance due to the leakage effect. So last, I would like to compare 2 different chokes or 2 different winding styles of one product, which has 51 microhenries of inductance. Both of them, on the left side, the one has a bifilar winding, and the right side is a sectional winding. So both have equal number of turns, and therefore the same main inductance. But if I look at the impedance graphs, then we see the difference. Not for the common mode impedance, the curves here lie on top of each other, but for the differential mode, for the sectional case, the differential mode impedance is much higher compared to the bifilar winding choke. And if I select, for example, at 1 megahertz and look at the values of each graph at this frequency, then I can read the value from the graph and put it to the equation which I've showed you before. So the inductance can be calculated by dividing the impedance by 2 pi times the frequency where I have read the data from the graph. So in this case, 1 megahertz. And for this specific case, if I do the calculations, then I get roughly 48 microhenries for the main inductance, which of course is inside the tolerance band for 51 microhenry nominal. And for the two differential mode impedance curves, first the sectional one, that's 20 ohms. And this gives me a value of roughly 3 microhenries. And if I use a bifilar wound choke, then it's only 0.65 ohms at the same frequency, and this is already much smaller value due to the bifilar winding. So we are in the nanohenry range now.
Clickable links are available in most podcast streaming networks. You can find the entire line of Worth Electronic common mode chokes available at www.we-online.com/CMC. This podcast was taken from a recent Worth Electronic webinar. To view the materials and replay the webinar on demand, visit www.we-online.com/webinars or click the link attached in this podcast. You're listening to Worth Electronics What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.